Two sides of an isosceles triangle are equal, so the ticks on the sides indicate the two equal sides. Now the third side does not have to equal the two sides. If all three sides are equal, we have what is called an equilateral triangle, and we will cover that in another video. For now, we just need two sides to be the same. The third side can be any length. Now, the angles opposite the two equal sides are equal. So here is the angle opposite the side here, which I'm calling A. So I'm using small a for the side and capital A for the angle opposite that side. This is the notation that we use in trigonometry. But of course we can use it here also. And here we have an angle that's opposite this side here. So if this side is small b, we call this angle capital B. Now we're not interested in the angle up here. This angle up here is opposite this side down here. We're not interested in it. Now I can move this triangle around and you can see that the values are getting updated, but I've set this triangle up so that it's always an isosceles triangle. So the two sides are always equal to each other, and as you can see the two angles are equal. Now we are going to prove that these two angles are equal. So we're given an isosceles triangle, we're given two equal sides. We are going to prove that these two angles are equal. Sometimes these two angles are called the base angles of an isosceles triangle, but they don't necessarily have to be on the baseline of the triangle. We could orient this triangle in a different way, of course. We could have it like this. To prove that angles A and B are equal, we draw in this line here, which is perpendicular to this side. Its length is h. Because it's perpendicular to this side here, these two angles are equal to 90 degrees. I'm calling them D and C. So we've two right angle triangles formed, and whenever right angle triangles come into a construction, we should apply Pythagoras. So the square of the longest side of this right angle triangle, that's b squared, must equal the sum of the squares of the two short sides, that is m squared plus h squared. Similarly, for this right angle triangle here, the squared hypotenuse of it, that is a squared, is equal to the sum of the squares of the two short sides, that is n squared plus h squared. Now we can make m squared the subject of this equation. M squared equals b squared minus h squared. Bring the h squared over. But since we're given that a is equal to b, in other words we're given an isosceles triangle, we can replace this b squared, or this b, with a. So we see that b squared minus h squared equals a squared minus h squared. However, if we look at this equation here, we can make n squared the subject of it, and we see that n squared equals a squared minus h squared. So a squared minus h squared is n squared. So we can see that m squared equals n squared, and if we get the square root of both sides, that means that m must equal n. So we see that not only is this line here perpendicular to this side of the triangle, it also bisects it. So we could call this line a perpendicular bisector of this side of the triangle. So we can indicate that with these dashes. Of course, we don't put two dashes for segment M, because then it would imply that it is the same length as segment B. So we have to have a different number of dashes here to distinguish it from the two other equal sides. Now notice that we have two triangles whose three sides are the same. The three sides of this triangle are B, H and M. The three sides of this triangle here are A, H and N. But A is equal to B, H is obviously equal to H in both triangles, and we've just shown that M is equal to N. So the three sides are the same, so that's one of the conditions for triangles to be congruent. We abbreviate that condition as SSS, standing for three sides the same in both triangles. So if the triangles are congruent, it means they're equal in every way. So in particular, it means that the remaining angles are equal to each other. Now, which angles are equal? Well, we take the corresponding angles, that is the angles opposite the same equal sides. So we can see that H is opposite angle B, and side H is also opposite angle A in this second triangle. So that means that A and B are the corresponding angles. So A must equal B. And that's the end of the proof. Of course, we could go further and conclude that these two angles are the same. So not only is this line H a perpendicular bisector of this side of the triangle, it also bisects this angle up here.